Okay, so I have the great pleasure of introducing Akhil Mathew from the University of Chicago. We will give his third and last lecture on new advances in syntomic cohomology.
Okay, yeah, thank you very much. So this is my third lecture on this mini course on syntomic cohomology. But actually, today's talk will be mostly independent of my last two talks yesterday. So today I wanted to talk about essentially what we call F smoothness in the paper with Bhargav Bhatt, and it's some sort of mixed characteristic analog of the Cartier isomorphism. So let me get started. Let me start by maybe reviewing the original Cartier isomorphism. So let R be an FP algebra, and so then we have the following construction. So we can consider de Rham complex, the algebraic de Rham complex of R over Fp, and we can take the cohomology of that. So that's so the de Rham complex is a commutative differential graded algebra. So the cohomology is a graded ring. And the construction is that there's a map called C inverse or inverse Cartier from the graded algebra of differential forms of R over Fp to the cohomology of the de Rham complex. So here we just have differential forms, and over here we have the cohomology of the de Rham complex. And explicitly, this map is so it's carrying, for example, the class of R to the class R to the P, which is a cycle in the de Rham complex in H0. So this is a let me continue. And the class of ds to s to the p minus 1 ds. So that's supposed to be, in quotes, it's d of s to the p divided by p. And this is for r, s in the ring R. And so then I guess one has to check that this defines a map of graded algebras, and this is well defined. And so then there's a theorem, following basic theorem, which is that if R over Fp is regular Noetherian, then C inverse is an isomorphism. Okay, so let me just briefly recall the proof of this theorem. Or a proof of this theorem, I should say. So proof is that you can check directly. So first is that you can check directly for a polynomial ring. And then you can observe that both sides étale localize, and then you deduce it for any smooth FP algebra. And now, since R is regular over Fp, R is a filtered colimit of smooth Fp algebras by Popescu's theorem. So R is in smooth. Popescu's theorem, and so then you can deduce C inverse as an isomorphism for R. Okay, so that's a proof of this theorem, and so essentially the goal of today's talk is to formulate and prove an analog and mixed characteristic of the above theorem, and also explain the application to syntomic cohomology as in the previous two lectures. And the idea is that it's supposed to be somehow formally similar to this theorem. But if you look at the proof, one thing, so much of the proof is pretty formal and works in a mixed characteristic setting, but it's no longer going to be true. Sorry, so maybe I should say that, so the analog and mixed characteristic is going to be that regular rings satisfy some analog of the Cartier isomorphism, and so it's not going to be true that regular rings are in mixed characteristic are going to be in smooth over Z or over a DBR or something. So one isn't going to be able to argue in quite the same way. And actually here it was sort of helpful, I'll come back to this, to observe. So this was something I learned from Jacob Lurie, which is that you can prove the above theorem, the Cartier isomorphism for regular FP algebras without using Popescu's theorem. So you can prove the above theorem without Popescu's theorem with a slightly longer argument. So without using inch-smoothness, with the slightly more elaborate argument. Sorry. And somehow this is the pattern. Well, somehow you. So I will essentially explain this in the mixed characteristic setting. But if you're curious, this remark is explained in some detail in an equal characteristic in 9.5.6 of the paper of our joint papers with Lurie and myself on the de Rham-Bhatt complex. So essentially, it's sort of going to be an analog of an analog of this one. Okay, so that's a side remark for now. Okay, so now that we have so now that we know the Cartier isomorphism for regular FP algebras, then a natural sort of question you can ask is which other FP algebras satisfy the Cartier isomorphism? Natural question is which other FP algebras satisfy Cartier? And so you can turn this into a definition. So there's the following definition, which was given in work by Kelly Morrow and Kurtz Strunk-Tama. And the definition is that R over FP is Cartier smooth so two conditions. First condition is that the cotangent complex of R over FP, this is something living in the derived category of R, and the condition is that it's flat. It's a flat R module. So it's in degree 0. Well, first of all, it's in degree 0, so that means the cotangent complex is the same as the module of Kähler differentials, and is a flat R module. And second is that the map C inverse, which again is defined for every FP algebra, is an isomorphism. So they make this notion of Cartier smoothness. So okay. So what are some examples of this notion? Well, first of all, any regular FP algebra, any regular Noetherian FP algebra. So that, well, I guess the same argument that I described above also shows that the cotangent complex is flat of R over FP, but this is in fact something you can also prove directly without appealing to Popescu's theorem of insmoothness. But okay, so regular FP algebras, and but there are lots of sort of non-Noetherian examples, which is one of the reasons this definition is useful. So for example, perfect FP algebras, and you can push this a little bit further. You can say smooth algebras over perfect rings, smooth over perfect algebras. There's also this a condition that I think has appeared in the literature, for example, in crystal and Dieudonné theory, which is this condition of having a p-basis. So let's say algebras which are relatively perfect over a polynomial FP algebra. So meaning that the relative Frobenius is an isomorphism. And this is called a p-basis. So these are also Cartier smooth. And one important example, so this is due to Gabor Romero and Gabor, which is valuation rings. So valuation rings over FP. So valuation rings over FP are Cartier smooth. So I guess this should follow from some local uniformization, but they're able to prove it directly. Okay, so let me also remark that, okay, so let me scroll up for the definition of Cartier smoothness. It's two conditions. The first condition is this condition on the cotangent complex. And the second is this C inverse being an isomorphism. And the remark is that you actually need both conditions. So this remark, so this is due to Bhatt and Gaber. And there's an account on Bhatt's website. So it's possible for an FP algebra to satisfy one but not two. And specifically, there exist algebras such that R is imperfect, sorry, R is semi-perfect, meaning the Frobenius is surjective, but not perfect. So imperfect with the cotangent complex of R over Fp being 0. So this will not be Cartier smooth. And the reason is that the inverse Cartier map, the C inverse map, is going to be the Frobenius in degree 0. I mean, so the de Rham complex is just R in degree 0. But the inverse Cartier map from R into the de Rham complex is the Frobenius, so it's not an isomorphism. So yeah, so this notion is a little bit subtle for that reason. Right, so why is this notion useful? Well, there are a couple of reasons. So one reason is that for any Cartier smooth FP algebra, the theory of the de Rham-Witt complex is well behaved. So the theory of the de Rham-Witt complex behaves, I think, essentially as nicely as it behaves in the case of smooth algebras over a perfect field. And well, I guess the theory of the de Rham-Witt complex is closely related to the Cartier isomorphism. So this is not surprising. And then two is that there's a nice description of the syntomic complexes of Cartier smooth FP algebras. And so this is a theorem. So this is, again, this is in Kelly Morrow and Kurt Strunk-Thelma. So if X is spec R, and R over Fp is Cartier smooth, then if you look at the syntomic complex Z mod P to the n twisted by I sub X, so again, that's a, so as in yesterday's lectures, that's an object of the derived category if étale sheaves on X. And it's exactly given by Wn omega I log sub X shifted by minus I. So this is exactly the same formula. So it's exactly the same formula as if X is smooth, say over a perfect field. So yeah, so the theory of syntomic complexes for Cartier smooth algebras behaves exactly as it does for say smooth FP algebras. Right. So this is so one reason this is useful for them is that they are able to, well, in particular they apply this to valuation rings, and they're able to do some. So in particular, this is they're able to compute the syntomic complexes of valuation rings over FP from this, and they have some sort of nice K-theoretic applications of this. And so the goal is to have sort of a mixed characteristic analog. Okay, so the first thing is that I want to reformulate this notion slightly of Cartier smoothness in such a manner that it will have a nice sort of mixed characteristic analog using prismatic cohomology. So let me reformulate. So again, right, so R is an FP algebra. So then we can associate to it the L omega of R over FP. This is the derived de Rham complex of R over FP, so as in work of Elucy and Bhatt. So specifically, or more specifically, this is defined by starting with the classical de Rham complex for polynomial FP algebras, and then extending to all FP algebras by animation or Left-Kahn extension. So it's the animation of the usual de Rham complex for polynomial. And right, so this is equipped with some structure. So this is equipped with this derived de Rham complex. It is equipped with at least two important pieces of structure for this. So first, it's equipped with an increasing filtration called the conjugate filtration. Which I'll write as Phil lower star of L omega R over FP. And this is always an exhaustive filtration, so it converges to the derived de Rham complex. And the conjugate filtration is, it's a Left-Kahn extension of the Posnikov, it's the animation of the Posnikov filtration in the case of polynomial algebras. And then there's the Hodge filtration. So this is a descending filtration. L omega of R over FP greater than or equal to star. And this is the animation of the naive filtration. So it's a naive filtration, or Hodge filtration for polynomial rings, and then you Left-Kahn extender animate it. And this is not always complete. It's not always convergent. Meaning that the inverse limit of the filtration is not necessarily zero, or the and in both cases, the associated graded terms are, well, by the Cartier isomorphism, the ith associated graded is given by the ith wedge power of the cotangent complex of R over FP, and with a shift by minus I. So yeah, so this is sort of the format. They have these two filtrations. Right, and so I guess the point is that it's possible to formulate the notion of Cartier smoothness in terms of this derived de Rham complex in these two filtrations in sort of a clean way. So, so let me state the result. So proposition. So R over FP is Cartier smooth if and only if the following two conditions are satisfied. So first of all, for all integers I, negative integers, the map from the ith stage of the conjugate filtration well, you have this map, and the condition is that the fiber of this map, so the fiber is naturally going to live in D of R. Well, so you can consider, right, so here I'm considering L omega of R over FP as a module over R, and I mean, this is somehow implicitly using the Frobenius if you think in terms of de Rham complexes. But it has fiber in D of R with Tor amplitude in degrees greater than or equal to I plus 2 for each I. So this is the first condition, and this first condition is really equivalent to this flatness of the cotangent complex. So if you sort of unwind the definition of the conjugate filtration, this is exactly the flatness of the cotangent complex. And then the second condition is that the derived de Rham complex is Hodge complete. So the Hodge filtration. So maybe I should say it this way. So condition one is exactly the flatness of the cotangent complex. And then if you're given condition one, condition two is exactly saying that the derived de Rham complex is the sort of actual de Rham complex, the explicit chain complex. So given one, two is the statement that L omega of R is the actual de Rham complex. because the Hodge completion, well, I guess one checks that the Hodge completion is going to be the actual Durham complex in this case. That's essentially how you prove for this theorem. Okay, so this is a slightly, maybe slightly more complicated way of formulating reformulating the notion of Cartier smoothness in terms of the derived Durham complex and these sort of two pieces of this conjugate and Hodge filtration elements. So the reason to formulate it in this fashion is that these objects have analogs in mixed characteristic thanks to the development of prismatic homology. So sorry, maybe I should still keep this. So right. So these have analogs in mixed characteristic. Right. So how do we formulate these analogs? So first of all, let me just work with quasi-syntomic rings throughout. So let R be a quasi-syntomic ring. So now let me scroll up perhaps. So as in yesterday, so we have the prismatic complex of R, prismatic cohomology. This is now going to be some object in the p-complete derived category, and it comes with a Frobenius phi endomorphism. And this Frobenius, it's naturally a filtered map. So if we take the Nygaard filtration on the prismatic complex, and if we take the I-adic filtration on the prismatic complex, where I is the prismatic ideal, then we have a map of filtered complexes. Well, essentially, by fiat, the Nygaard filtration is exactly the filtration that's making the Frobenius divisible. And we can consider what happens on each of the associated graded pieces. Okay, so we have this map of filtered complexes, and on Ger I, we obtain a map, which I'll call phi sub I, and it goes from the ith associated graded piece of the prismatic complex. So I'm writing that as n. Sorry, there's a question. The Tor amplitude, I think I'm using cohomological conventions. I hope I didn't. Sorry. Yes. So yeah. It's in cohomological conventions. Okay. Yeah. Thank you. Okay. So on Ger I, there's a map from the ith stage of the Nygaard filtration to, well, I want to write this as I to the I mod I to the I plus 1. And another name for that is the Hodge-Tate homology of R, broken and twisted by I. So you have this map. And right, and so the observation, or this is part of the theory, is that this map phi sub I recovers for R over FP, for the case where R is an FP algebra. This recovers the map from the ith stage of the conjugate filtration of the derived Durham complex to the derived Durham complex of R over FP. So for an FP algebra, Hodge-Tate homology in this prismatic theory is the same thing as derived Durham homology as previously defined. And this phi sub I, this map on associated gradients is exactly picking out the ith stage of the conjugate filtration. So this is directly an analog of the previous construction. Okay, so now let me make the definition. Let me keep this visible, perhaps. So definition, a quasi-syntomic ring R is F smooth if we have the following two conditions. So first of all, for each I greater than or equal to 0, the fiber of this map phi sub I, which again is going from Ni of prism R to prism Hodge-Tate of R, twisted by I. And when we take this fiber, it has p-complete Tor amplitude. So p-complete Tor amplitude means that you have the Tor amplitude condition after you extend scalars to R mod p. So it has p-complete Tor amplitude. In degrees, at least I plus 2. Right, so that's an analog of the first condition in Cartier smoothness. And the second condition is, well, so the analog of Hodge completeness. Now we have to say that the Nygaard filtration is Hodge, is complete. So, and in fact, we need it not only on prismatic homology, but on all the Brocas. So for each I, the Nygaard filtration on prism of R twisted by I is complete. So this is exactly analogous to the condition that the Hodge filtration on derived Durand homology is convergent. Okay. So this is the definition. And so let me give some examples. Right. So first of all, for R over FP, this is exactly the same. This is equivalent to the notion of Cartier smoothness. Right, but so there are also some other examples. So for instance, if R is perfectoid, then R is also F smooth, because in fact in this case these maps phi sub I are actually isomorphisms, and one can also check. I mean, one can also see the completeness of the Nygaard filtration, because essentially it's some. It's very, I guess it's very explicit in this case. The prismatic homology is ANF, and yeah, okay. Okay, so maybe more generally, if R is smooth over a perfectoid, then R is F smooth. And this is right. So if something is smooth over a perfectoid, then this is in the setting of relative prismatic homology. This is absolute prismatic homology, and then this follows from the Hodge-Tate comparison, as in the article of Bhatt-Morrow-Scholze, prisms and prismatic homology. Right. Okay, and so actually, so for algebras over a perfectoid ring, this condition of F smoothness has also been studied by Bui, and there's the following fact. So this is, for example, in this case. So if we have a perfectoid ring R0, then it's possible to make very explicit this condition of being F smooth. Sorry, for algebras over R0. So then a ring R over R0 is F smooth if and only if we have the following two conditions. Well, first of all, if we take the cotangent complex of R over R0, and I mean everything is P complete, then this is P completely flat. Right, so maybe to be careful, I'm going to assume everything is quasi-syntomic to begin with. So yeah. And second, if we take the relative derived Durand homology of, or derived Durand complex of R over R0, then this is, so again, I P complete everything, and then this is everything in the P complete category is Hodge complete. So this is exactly analogous to, right, so this is exactly analogous to the case over FP. So over FP, this was equivalent to Cartier smoothness, this is a reformulation of Cartier smoothness, and this actually works over any perfectoid. Right? Okay. Right. So another example is ZP itself. Another example of an F smooth ring is the ring ZP. And this is essentially contained in the APC paper. This is essentially explained in the APC paper. But in fact, in this case, you can make everything really explicit. You can make these objects very explicit. So as I recall this a little bit from master, let me say it again. So in this case, if you consider the cohomology of the Nygaard pieces of the prismatic homology of ZP, but with mod P coefficients, then you can compute this explicitly. It's a it's an exterior algebra on a class alpha, tensor a polynomial algebra on a class theta. And here, alpha, so this is a bigraded ring because of the cohomological and the internal grading, and I'll write the cohomological grading first. Alpha is in bidegree 1 comma p, and theta is in bidegree 0 comma p. Furthermore, the cohomology of, if you take the Hodge-Tate cohomology of ZP, again with all the Broikis and twists, mod p, this is another bigraded ring, and it's exactly the exterior algebra on the same class alpha, and instead of a polynomial ring on theta, it's a Laurent polynomial ring on the class theta. And so you have a map of bigraded rings, which is coming from the divided Frobenius. And so alpha smoothness is saying that that map is sort of a range of, that's like an isomorphism on Turner amplitude and some range. And you sort of see that here directly from writing these out. So. Right, and so I should also say that, right, this is something that's that follows pretty directly from the Stacky approach to prismatic cohomology, because you can identify, well, at least for the Hodge-Tate cohomology, you can identify very explicitly with the cohomologies of stack, which is classifying stack of a group scheme, and then you can compute the coherent cohomology pretty directly. So I think also, right, so one also has to check this Nygaard completeness, which is a little bit subtle. But this is also explained in APC, and I'll also explain it sort of later in the talk. Right, so this is somehow an important example, and actually, so this example kind of it leads to the following observation, which is somehow useful, which states that if R is any F smooth ring, so if R is F smooth, then this class theta this class theta, so right, so here, let me just write it again. So here theta is something that lives in H0 of the pth Nygaard stage of the prismatic complex of ZP with mod p coefficients. And the observation is that if you have an F smooth ring, this operator theta, that the Nygaard pieces of the prismatic cohomology of R are somehow periodic in some range via this operator theta. So if R is F smooth, then multiplication by theta, which goes from the ith stage of the prismatic complex of R mod p to the I plus p stage of the prismatic complex of R mod p, then the statement is that has fiber, this map has fiber with Tor amplitude in degrees at least I plus 1. So in particular, as I gets larger and larger, these sort of stabilize. And in fact, they stabilize to the Hodge-Tate complex of R with mod p and with Broikis and twisted by I coefficients. So this is saying that somehow theta is on these Nygaard pieces is sort of periodic. And this is sort of a technical observation, but it actually is pretty useful in our paper. And so it's actually useful for proving some of the basic facts about F smoothness, which is that these Nygaard pieces for an F smooth ring have this sort of property. So there's a question from Gabor.
So I'm a little bit confused about the mod p notation. So here you are doing something over R and then reduce all everything mod p, or you do something for R mod p?
Okay, thank you. That's yeah. So just to be clear, I mean here I take the Nygaard piece of R and then I reduce that complex mod p.
Yeah, but then you reduce it and then you view it. Then it is a module over R mod p, but you have to take R mod p in a derived sense, or in the, so when you do Tor amplitude now, what is it? Is it over R or over R mod p? Or
right, I was actually saying over R. So yeah, for simplicity, maybe a better yeah. I mean, you could also say it for amplitude in degrees at least I plus 2 if you say it as a module over the derived R mod p.
Okay, so I was confused with derived R mod p. Okay, so this is over R. Okay, thank you.
Yeah. Actually, yeah. So we call this weak F smoothness in the article, but it's probably a little bit better definition is sort of along the lines of what you said, that that you do this, you consider this as a module over R derived mod P. But in any case, it's just more of an auxiliary notion that we used. Okay, so now let me explain some properties. So that this notion of F smoothness is somehow robust. So proposition, the class of F smooth rings is well, first of all, it's closed under étale localization. Well, it's étale local and it's closed under étale extensions. Étale local. Right, and I guess more generally, it's stable under passage to a smooth algebra. Well, in particular, a polynomial algebra. And finally, it's closed under filtered columns. Right, and let me just comment that this is so there's some sort of basic stability properties. Let me just comment that there's something to. Okay, so actually, sorry, there's a question in the chat. So the question is it P complete Tor amplitude? So it's P complete Tor amplitude in the sense of the BMS2 article, meaning that so if you have an object of D of R, you say that its P complete Tor amplitude is basically the Tor amplitude after you extend scalars to R mod P and consider it as an object of D of R mod P. Okay, so yeah, so this is closed under filtered columns, and right, so there's something a little bit subtle that's happening here, which is that there's this condition of Nygaard completeness, and completeness is saying that some inverse limit is 0, and a priori that's not going to pass through a filtered column. And there's an observation that one makes here, which is related to this observation about theta being sort of a periodicity operator, which is that if R is F smooth, right, so then if you take the Nygaard filtration, well, not on the prismatic complex of R, but on the Hodge-Tate complex of R. And, well, so you define that by reduction on the Hodge, on the prismatic ideal. And so actually we discussed this a bit in the article. So if you consider the Nygaard filtration on the Hodge-Tate complex, and then if you reduce it mod P, then this is somehow uniformly pro-0. Right, so F smoothness is going to say that this has to converge to 0, the completeness of the Nygaard filtration. But actually, if that's true, it's going to be somehow uniformly pro-0, and uniformly means independent of the choice of F smooth ring. So this is useful because it tells you that, for example, it's going to be stable under filtered columns because it's not just completeness, but it's some sort of very strong completeness. Okay, so yeah, so this is helpful in improving these sort of stability properties. Okay, so maybe now let me state the theorems. So essentially, I wanted to explain two theorems, or say a little bit about two theorems. So first, let me call this theorem A, which is a connection with syntomic complexes. Sorry, there's another question from Bhargav.
Just a moment. Okay, so this uniformly pro-0, is it for the full complex, or just in some cohomology degree in relative to some dot? I mean, so there is also a dot here and the cohomology degree. So is it uniformly relative to what? To
sorry, yeah, thank you for pointing that out. So sorry. So when I say uniformly, when I say pro-0, I should be more careful. This is really in any range of degrees, in any cohomological range.
So it means that for any cohomological range, it is uniformly, but it is not the case that the maps are transition map becomes 0 in the derived category for large.
Yes. That's right. Thanks for pointing that. Yeah, so it's on the level of, say, cohomology groups in some range. Yeah, so I think it'll be true after you truncate to each level.
Okay, so if you take a bounded truncation and you fix the star, then you have a uniformly pro-zero independent of the choice of R.
Right. I think it'll be independent of the choice of the twist. I mean, sorry. I guess the example would be like, I mean, if you take the Hodge filtration, I mean, it'll be like the Hodge filtration on. I mean, it'll be like the naive filtration on a co-connective complex, essentially, like, or the Hodge filtration on a Cartier smooth FP algebra. Then it's just the naive filtration on the level of complexes, and it's not going to be quite that, but I think again up to some something bounded, it's going to be that. Yeah, but yeah, thank you. So this, when I say pro-zero, I should be careful. Pro-z in the derived category, I really mean on the level of each cohomology group, and but that's enough for the stability under filtered colimits. Thanks. Okay, so so let me explain the theorem. So first,
question in the room.
Oh yes.
Yeah, just didn't catch that one. In the last theorem, you claim the class of F smooth rings is closed under. The first one is étale extension. I wonder what does it mean by étale extension, because the second the one tells me it's closed on the smooth algebras.
Right. I guess I didn't. So I guess I was redundant. I could just say that it's somehow yeah. So let me put it this way. It's okay. So you can say it a little bit stronger. It's closed under sort of P completely flat, relatively perfect maps. But in particular, it's étale local, and yeah. So sorry, I think what so I was a little bit redundant here. So thank you for catching me. In particular, I wanted to say that if you have a ring and a quasi-syntomic ring and you want to check that it's F smooth, you can check it on, in particular, say the strict tensorizations or Zariski localizations or something like that. So again, there's a little bit of subtlety because of these issues of completeness, essentially, but and that's why I wanted to mention this observation. So, okay. Yeah, thanks. Okay, so first is the relation with the syntomic complexes. So this is proved. Well, it's in our article, and over a perfectoid base. This was also proved by Bowie. And the statement is the following. So if R is p-torsion free and F smooth, right, so then the map from the syntomic complex of R, let's say with mod p coefficients, to the syntomic complex of R adjoint 1 over p is an isomorphism on Hj for j less than I, and it's injective on Hi. It's injective on this cohomological degree. Okay, so let me scroll up. So that's the relation with syntomic complexes, and then there's theorem B. So this is in our article. So if R is a p-complete Noetherian ring, then R is F smooth if and only if it's regular. Right, and yeah, so I think there's a heuristic that, for example, I've learned from Bhatt and some of his lectures that that in this prismatic theory there's some things that should work well for. I mean, that there are things that should work well for regular schemes in the sense that there's some sense in which regular schemes should behave like smooth schemes, or should have some sort of smoothness that can be visible in prismatic homology. And so this is maybe one instance of this idea. Right. So theorem in A and theorem B, if you combine them, they give you most of the theorem I explained yesterday about the syntomic complexes of regular rings. The further thing that one has to do is to identify what happens on this top cohomological degree. That's actually a separate argument that uses some of the results on the block Kato filtration on p-adic nearby cycles. And there you can actually reduce to smooth C algebras. So that's a slightly different argument, but for that last stage for the topological degree. But otherwise, these two results imply what I explained yesterday. Okay, so I guess for the rest of today, for the remaining 15 minutes, I wanted to mostly talk about theorem B. If I have time, I'll say a little bit about theorem A. Okay. Right. So yeah. So theorem B is supposed to be an analog of the fact that regular FP algebras satisfy a Cartier isomorphism. Okay, and so the way that we prove theorem B, so I'm scroll up. So the way that we prove theorem B is to prove the following proposition. So if R is in syn and X in R is a non-zero divisor, then we have the following criterion for R to be F smooth. So if R adjoin 1 over X and R mod X are F smooth, then the conclusion is that R itself is F smooth. Right, I guess I should say that if we have a non-P complete ring, we say that it's F smooth if it has bounded P power torsion and the P completion is F smooth. Okay, so this is a proposition. This is a criterion for F smoothness we proved, and right. So this is going to imply theorem B, and the reason is that to prove theorem B, well, first of all, you can reduce the case where R is local because, as I mentioned, you can check it on localizations, and then you can choose an element part of a system of parameters. And by Noetherian induction, you can assume that either when you've inverted that element or when you've modded out by that element, you have something F smooth, and then that proves the theorem. So essentially, this argument is going to say that you can reduce to the case. Well, this Noetherian induction argument is going to tell you that you can reduce proving F smoothness to the case of a field of characteristic P, and for a field of characteristic P, it's F smooth because you can choose a P basis, for example. So by Noetherian induction, localization, and reduction to field of characteristic P. Sorry, there's a question from Oprah.
Well, this is one direction of theorem B. The other one, that regularity is implied by F smoothness, requires something else.
Yes, thank you. Sorry, it implies this direction, but the other direction is easier, and actually it doesn't need. Thank you. Yeah, sorry. This implies that the direction that regularity implies F smoothness. The other direction is actually a little easier, and you don't need F smoothness. You really need this sort of weak F smoothness or special case of that. So maybe I won't have time to do that. But okay, so right. Yeah, thank you. So okay, so let me also comment that this argument also reproves the Cartier isomorphism for regular FP algebras without using insmoothness in that case. And so this reproves Cartier for regular FP algebras, and in this form, it's essentially, I think, the argument that what I learned from Lurie, and that's in our joint paper as well. Okay, so yeah, so this is sort of a proposition. Okay, so let me say something about the proof of the proposition. So this condition of F smoothness is right. It's in particular some sort of Tor amplitude condition, and you can check the Tor amplitude. In general, you can check these Tor amplitude conditions by first inverting an element, a non-zero divisor, or modding up by the element. And so to prove this proposition, essentially, you need a way of relating the prismatic complex and these Hodge-Tate complexes of of R and R mod X. So the prismatic complex of R and R adjoint 1 over X is sort of easier to relate because it's an étale extension. But yeah, so you need something for a non-zero divisor. And so to prove the proposition, we prove the following results. Right. So for each I, there are fiber sequences where you have that relate the prismatic complex of R, reduce mod X with the prismatic complex of R mod X. So let's say the Hodge-shaped complex of R twisted by I, modulo X, mapping to the Hodge-shaped complex of R mod X twisted by I, and the Hodge-shaped complex of R mod X twisted by I minus 1. And then actually also on Nygaard completions, because we need to talk about Nygaard completeness. And on the individual Nygaard pieces, so on Ni of prism of R mod X to Ni of prism of R mod X to Ni minus 1 of prism of R mod X. And so this is going to imply the previous proposition because it, well, by these fiber sequences. Well, the previous proposition is, well, going to reduce to understanding the map from prism of R or Ni prism of R to prism bar of R twisted by I when you reduce that map mod X. And this lets you sort of do that in terms of the prismatic complexes of R mod X itself. Yeah, and so I think at least the first fiber sequence, for example, one can sort of do this using the Hodge-Tate stack, as in the papers of Lurie and Drinfeld. We sort of do it by hand also to do the second fiber sequence, but not, sorry, there's a question. It says a fiber sequence of filtered
excuse me, if you
Yes.
could raise your hand and ask the questions, because we cannot read the questions in the room, okay? So next time, please raise your hand to ask the question.
Oh, sorry, so I can reread the question. So the question is this a fiber sequence of filtered complexes with the Nygaard filtration? I think not quite. So I'm not sure. I think that, so hopefully there's a way of, of really, so there should be a way of formulating all this in a stack theoretic fashion that would really explain, explain this more directly. But I think, yeah, I think this is the statement right now. And I guess, yeah, so the issue is that the comparison between sort of the Nygaard filtration, as in, say, Scholze, and the stack theoretic approach has not yet been, has been at least announced by Lurie, but it's not yet been documented. So essentially we do it by hand in the article, and it's not so hard actually. Okay, so but yeah, so that's essentially the argument. I mean, that's essentially the argument for regular rings being F-smooth. And let me remark that it's right. So first of all, so the other direction that F-smoothness implies regularity is a little bit easier. And in fact, you don't need, for example, this condition of Nygaard completeness is not going to be used over there. But for example, here we're showing that regular rings have this Nygaard completeness property. And right, so a remark is that this should be related, and it's at least sort of reminiscent to work of Saito and Hochster-Jeffreys, giving a criteria for p-complete Noetherian rings to be regular in terms of something called Frobenius Witt differentials. So actually I don't completely understand, haven't completely understood the relation yet, but just wanted to mention that. Let me also just mention a couple of other applications of the fact that regular rings are F-smooth, and in particular the Nygaard filtration is convergent for regular rings. So there's the following corollary, which is also in the article, which is that if let R be a regular local ring, with perfect residue field. And let me suppose that R mod P is F finite, so finite over the Pth powers. And then the conclusion is that the Hodge-Tate cohomology of R lives in cohomological degrees at most the Krull dimension. So this was suggested in this was asked as a question in the Bhatt-Lurie prismatization article. And I think if you try to approach this, I mean, so it's not hard to prove the bound with dimension of R plus 1, but if you use Nygaard completeness, you can also sort of improve this by 1 and get it to the dimension of R. So this is another sort of application in our article. Okay, so maybe I have 5 minutes, so let me maybe just end by raising a couple of questions about this notion of F smoothness. So I'd be very happy to sort of understand this, have a better feel for this notion, and so maybe let me end with a couple of questions. So a couple of natural questions about F smoothness. Right. So one question is this valuation ring question. So valuation rings over FP are F smooth, and this turns out to be pretty useful. And so one could naturally ask, are valuation rings in general F smooth? And right, so I guess this has been proved work in progress of Bowie over a perfectoid valuation ring. But hopefully it's true for general valuation rings. And another question would be to have sort of a closer relation with prisms. So, I mean, again, the idea of F smoothness is some sort of notion of something like regularity for non-Noetherian things. And another sort of question is that given a prism A comma I with A p-torsion free and A mod P Cartier smooth, is A mod I F smooth. So this sort of feels like something that, I mean, so for example, if you have a complete regular local ring, then this would be an example of this. And so potentially this would give a more direct proof that regular rings are F smooth. So yeah, so maybe this will be sort of possible once also with sort of a Stacky approach. So okay, so these are a couple of questions. Yeah, maybe let me also just say, so finally in proof of theorem A, it's the strategy of proof, again, it's about comparing the syntomic complex of a p-torsion-free F smooth ring and of the generic fiber where you inverted P. And the strategy is essentially if R is F smooth, p-torsion-free, and in fact, you can reduce quickly to the case where R is P-complete. You consider the map of multiplication by V1, where V1 is this class I mentioned yesterday, from the syntomic complex of R to the syntomic complex in weight I plus P minus 1 of R. And you show that this map is an isomorphism in some range. And the stable limit of multiplication by V1 is given by the syntomic complex of R adjoined 1 over P by étale comparison. And so by étale comparison, this is enough. So to prove that this map is an isomorphism in some range, essentially you use the description of the syntomic complexes as this sort of fiber, mapping fiber, in the case where R is P-complete. Description of and then you use this fact that I mentioned at the end of yesterday, that V1 is somehow detected by the element, the sort of periodicity, is somehow detected by theta in the Nygaard filtration of the prismatic complex of ZP, and the fact that theta is a periodicity operator. So it's essentially some sort of linear algebra argument. And it actually was inspired by some arguments in the algebraic topology literature. topological cyclic homology. Okay, so I think I'll stop here. So thank you very much for your attention, and again for the opportunity to give these lectures.
Thank you very much. Are there any questions from the room first? Maybe I have one question. What applications do you see from this notion of F smoothness in other theories, maybe characteristic cycles, or I don't know?
I'm not sure. Yeah, I would be curious. I'm not very familiar. I mean, I think this notion came very naturally in trying to think about the syntomic complexes somehow. I mean, actually, yeah. So this notion of F smoothness, right? So I mean, again, it was sort of inspired by some algebraic topology, and in algebraic topology, when you consider topological Hochschild homology, there's a condition that frequently comes up for the cyclic conjecture, which is something that one often has on topological Hochschild homology, and this is essentially the condition of F smoothness was essentially the cyclic conjecture on graded pieces sort of made a little bit more quantitative using these BMS2 style motivic filtration. So that was where it was sort of originally motivated by. Yeah, I mean, I think that, I mean, for example, if one had, if one place where some of these notions are being used is in this work by ongoing work by Bachman, Elmonto, and Morrow on trying to study motivic complexes for singular schemes, defining and studying motivic complexes for singular schemes, and that work I think currently is mostly an étale characteristic and essentially relies on the F smoothness of valuation rings over FP, and potentially some of those results could be extended to mixed characteristic using F smoothness.
Thank you. And then from Zoom, maybe. If no more questions, then thank you very much for beautiful lectures. And let's thank you.